Hello everybody and welcome back to Algebra 2. Today we're going to be talking about 4-1 polynomial functions. Let's begin. So let's talk a little bit about the vocabulary for today. Write an S if the expression is in standard form and write N if it's not. In order for something to be in standard form, all you have to remember is that the exponents need to be decreasing as you go from term to term. So taking a look at the very first part, we have a 5 plus a 7x minus a 13x squared. And even though there is no variable in the beginning, that's really the equivalent of the x to the 0 power. And then the x by itself is really the same thing as x to the first power. So as you can see, we are actually increasing exponents, and that is why this is not considered a standard form. Again, in order for it to be standard form, it needs to be going down. It needs to be decreasing. Case in point, the second part. We have a 2, we have a 1, and then we technically have the 0. 2, 1, 0, that is decreasing. That's how we know it's in standard form. We have a 2, and then we have our 1. Once again, it is in standard form because it is decreasing. You don't have to have every single term with the proper variable. It's a-okay to skip over some exponents here and there. The most important part is that it needs to be decreasing from the start to the finish. So let's go a little bit more in depth with our vocabulary. Today we're going to be talking about polynomials. And some things that you might end up hearing me say are something like a monomial or a binomial or a trinomial. Alright, see, a polynomial is a monomial or a sum of monomials. And if you can see in the top right corner, you're going to notice that one monomial is basically anything that has its own term. So like a 3t is considered a monomial. RT is going to be a monomial, and the R cubed is a monomial. But if we were to put them all together, that's what creates that full out polynomial. All right, poly being the fact that there are many, and mono being the fact that there's just one. All right, circle the polynomials in this expression. Well, in order for something to be a polynomial, once again, you need to have separate terms. And more importantly, you can't have a variable in the denominator. If you have a variable in the denominator, it won't work. So if we take a look at the very first one, this is not going to be considered a polynomial because we have that t in the denominator. So we don't have to worry about that one. The very next one, we do have a 7g cubed, perfect, plus an 8g squared, that's fine, and minus 5. All of these will work because, again, we don't have to worry about dividing by a variable, which means that we know that that is correct. And the very last one, as you can see, we are blatantly dividing by a variable right off the get-go, which is why we know it's not a polynomial. That being said, on the last one, the real reason is also because, yes, we can take the x away from the 3x squared, and yes, we can take an x away from that negative 5x. But we can't take it away from the 2. So we would end with a plus 2 divided by x at the end, and that's why this is not considered a polynomial. Circle the graph that represents a polynomial. In order for something to be a polynomial, it can be written as a function. Now, this is a straight line, a linear function. It comes in the form of y equals mx plus b. That is one term, that is another term. There is no division by x values, or division by variables, and therefore, that first graph is in fact a polynomial. This right here looks to me like it's a quadratic, because it's a parabola, so again, it's going to be some form of x squared plus some form of x plus some number. We'll say 1, even though that's not necessarily true. But whatever this ended up being, regardless of the fact, we're not dividing by a variable. So once again, this is a polynomial function. And more importantly, it's passing the vertical line test each and every time, and that's why we're allowed to call it a function. And based off of the name that is given, we're talking about polynomial functions, and these do not pass the vertical line test, meaning that these are not functions. And since these are not functions, we aren't going to even worry about this last graph. The next little bit, write the number of terms in each polynomial. In order for something to be a term, it's basically going to be the spot that is separated by a plus or a minus sign, is how I like to think of it. So a 6 is one term. The negative 7x squared is another term because it's separated by that negative sign. And then last but not least, we have the 3x. So right here, I'm going to say that there are 3 total terms. You have a one term, 2 terms, 3 terms, 4 terms, and 5 total terms. So we're going to say that is 5 terms. we have 1, 2, 3, and 4, giving you 4 total terms. You can consider it based off of the things that are separated by plus or minuses. You can consider a term as however many monomials there are in the polynomial function that is given. But regardless of the fact, all you really need to do is just count up the things that are being separated by the pluses and the minuses. Now, before we start talking about this whole paragraph right here, let me explain one major thing, and that is the degree of a polynomial. What is the degree? Well, the degree is essentially going to be whatever the highest exponent happens to be. So if you look at the very first graph, they see that we have an x to the fourth, we have an x to the third, and we have an x to the, well, the understood first power. In this case, the degree for this problem is going to be 4, because 4 was the highest exponent given. Whereas if you look at the second one, we have an x squared and an x. Well, the 2 is going to be the degree because the 2 is the large exponent. The 3 is going to be the degree for this problem because, again, that is the highest exponent. It's also the only exponent, but it's the highest one. All right, so no matter what, the degree of the polynomial function that is given is going to be the highest exponent that is attached to the variable that we're working with. Usually that's going to be the x value. But anywho, let's get into the paragraph. The degree of a polynomial function affects the shape of its graph and determines the maximum number of turning points, or places where the graph changes direction. It also affects the end behavior, or the directions of the graph, to the far left or to the far right. A function is increasing when the y values increase as the x values increase, and a function is decreasing when the y values decrease as the x values increase. Essentially, that's saying if the y values are increasing as we go to the right, it's obviously going to make a positive graph, meaning it's going to go upward. All right. If it's decreasing, that means that it's going to be going down again as we're going to the right, which is why we have that downward shape. All right. So that's really all that's saying. The turning points. The most important part when it comes down to the turning points is the fact that depending on whatever the degree is, you know that the maximum number of turning points that could potentially happen is going to always be one less than what the degree is given. So the degree for the very first one is a 4, so the most amount of turning points that we can possibly have is 1, 2, 3. So this graph shows that we have the most that we can get. That being said, it doesn't tell you the actual number of turning points that we actually are allowed to have. It is strictly just the maximum. All right, so essentially, if we look down here, we can kind of see that, well, we don't really fully have a turning point. It always seems to be traveling up in that cubic function. You might make an argument that we kind of have a turning point right here and right there, but for the most part, it looks like it's constantly going up. Whereas the other cubic, the bottom right-hand graph, you can blatantly see there's one turning point right there because it's going down, then back up. And then there's another turning point right there because it's going from up to down. All right. So the maximum number of turning points that you can have is solely based off the degree minus 1. So let's talk about the endpoints. Looking at the endpoints, you can notice that there are two different types that you can possibly have. You either have the endpoints turning and going in the same direction, like you see in the very first two graphs, or they could be going in opposite directions. Again, this one starts going down while it ends going up, or it might start going up while ending going down. The important part comes with the degree once again, because if you notice, the degree for the points where it's going to be the same, where if it's starting down, it's going to end down, or if it starts up, it's going to end up, well, they're even numbers. Whereas the odd number degree will cause them to be going in opposite directions. And you can kind of see that over here. This is just a fancy way of putting, if our exponent happens to be even, the positive or the negative version, no matter what will happen, the endpoints will be traveling in the same direction. So if it's a positive graph, meaning it's kind of like the happy graph for a parabola, it's going to be going up and up. If it's a negative graph, meaning there's a negative number in front of the x squared, just like this one is shown, it's going to be going down, down. Whereas odd numbers will create the endpoints to be going in opposite directions. So If it's a positive, that means it's going to be increasing from left to right. So we're going to start at the lower of the numbers, and we're going to be just constantly going upward. And if it's negative, we're going to be starting at the high portion, and we're starting up, but we're going to be traveling downward. We're going to be going farther and farther negative, and that's what the endpoints will be for a negative graph. Problem 2. Describing the end behavior of a polynomial function. Consider the leading term of y equals negative 4x to the third power plus 2x squared plus 7. What is the end behavior of the graph? And can you circle the leading term of the ax raised to the n in the polynomial function? Well, essentially, all you're trying to figure out is, well, what's the beginning number? What is that number that is attached to the variable with the degree, or the highest exponent? In this case, the coefficient that is attached to the x value that has the highest exponent will end up being a negative 4. So in this polynomial, a, or the number in front of, well, the variable that we're talking about, happens to be negative 4. And since this is negative, and we know that the n, or the exponent, is a positive 3, meaning that it's going to be odd, we then know that since it's negative, it's going to be going downward. But more importantly, the odd means that we're going to be starting in the upward motion, and we're going to be ending down, because we have to end with its opposites. Now, if it was even, it would be down, down, but in this case, since it's odd, you're starting high, and you're going to be ending low. That's how you show that negative going down. Circle the graph that illustrates the end behavior of this polynomial. Well, this one starts low, goes high, so we know it can't be this one. This one is a negative graph. However, they're both going down, which means that this is actually going to be an even exponent, not an odd. So the only one that seems to work is going to be the end behavior that is up and then goes down, which happens to be the third and final choice. Circle the letter of the graph that is continuously decreasing, underlining the letter of the graph that increases and then decreases only. Well, if I had to underline something that is increasing and then decreasing, that would be something that is changing direction, and it's going to be changing direction once. So I'm going to go out on a limb and say that the graph B is going to be the one that is increasing and then decreasing only, because as you can see, it's going to increase from left to right, but then it's going to reach its vertex and it's going to drop all the way back down. That's causing that decreasing portion. Now we have to circle the letter of the graph that is continuously decreasing. In other words, there is no turning point. The very first one shows at least 2 turning points. The only one that doesn't really show a turning point is that third and final graph, graph C. So I'm going to circle that one as well. And you can kind of see it almost looks like it wants to change direction, but it actually fully doesn't. It just kind of slows down a little bit and then starts shooting more and more negative. Great job. Problem 3. Graphing cubic functions. What is the graph of y equals negative x cubed plus 2x squared minus x minus 2? And can you describe the graph? Underline the correct word to complete each sentence. The coefficient of the leading term is going to be negative. The exponent of the leading term is odd. Well, since it's cubic, it's a 3, so it has to be odd. And remember, the leading term is that if we were to write in standard form, it's going to be the term with the highest exponent. In this case, that's where the negative comes from, and the odd exponent. Therefore, the end behavior is going to be in opposite directions, which means that it's going to be going either down then up or up then down. But since it's going to be negative, we need to be going downward, so we're going to start up and we're going to end down. Circle the graph that shows y equals negative x cubed plus 2x squared minus x minus 2. If we're starting up and we end down, it's going to be the second graph, because notice we're starting in the higher portion, but we're just going to keep on traveling more and more negative. The end behavior of y equals negative x cubed plus 2x squared minus x minus 2 is going to be starting up and then ending down, and they're going to be, it looks like 2 turning points. You have one right there, and then it's a very quick another turning point. Problem number 4. Using the differences to determine degree. What is the degree of the polynomial function that generates the data shown in the table to the right? Well, given the information that we have right here, trying to figure out whether or not something is linear, quadratic, cubic, or quartic, quartic being a 4th degree, cubic being a 3rd, quadratic is squared, and linear is no exponent, that y equals mx plus b form. It would normally be kind of difficult to just kind of look at it and be like, yeah, you know what, this is a cubic function. But in this case, people started to notice a couple things. And that is, if we take the difference of the two numbers that are side by side one another, the y values that is, and making sure the x value is obviously increasing by 1 each and every time, you can then start to see a pattern. So the first difference would be, well, we have a 39, a -1, a -5, and you can kind of see where there's just subtracting everything out. So a -10 minus a -13 is really adding 13, so that's where you get the +3. And then you have the -1 and the -41 doing the exact same thing. All you're doing right here is just subtracting. Well, once again, we're just going to subtract. So we should have a 40, and this one is going to end up being a 4. We have a -8, a +4, and then we have a 40. Well, it looks like we're starting to get into a little bit of a pattern, but we're not quite there yet. We have a 36, a 12, a -12, and a -36. Once again, we're starting to get another pattern going, but it's, again, not really sure what we're doing with. All right, but if we do it one more time, you're going to notice that the difference will actually all end up being the same. So essentially, we know that since all of them happen to be the same on the 4th difference, we know that the degree of the polynomial is going to be 4. Meaning, if I were to figure out what this actual polynomial will be, it's going to end up being some form of the y equals the x to the 4th power. So again, all you have to worry about doing is just subtracting the y values that are increasing by 1 every x value. And when you do that, eventually, if you keep on subtracting them until you get to a point at which they are all the exact same answer, like the 24, 24, 24, however many steps that took to get to it is going to end up being the degree of the polynomial. And last but not least, we had the lesson check. Let's get going through this and let's end it nice and quick. All right, describe the end behavior of the graph of y equals -2x to the 7th power minus 8x. Underline the correct words to complete each sentence. The value of a in -2x to the 7th is going to be negative. Right? The a, again, is a number or the coefficient of the variable that we're talking, the leading term. Right? The exponent is going to be odd because 7 is in fact an odd number. And the end behavior, since it is negative and odd, we know that it must start going up and it must end going down because it's going to be going in a negative fashion. And since it's odd, they have to be going opposites. That's why it's up and down. And that is it, everybody. Great work. I hope everyone has a wonderful day. Stay out of trouble. Don't do anything stupid. And I'll see you guys in the next one.